Hi, my name is Siting and I'll be presenting alongside Herman, Junius, Zipin, Xavier and Nigel. Today we'll be talking about biofuels. Our agenda today will be introducing you to biofuels, sharing our justification, having a literacy review, explaining our biofuel experiment, showing our timeline, and last but not least, we will have a summary to sum up everything we mentioned today. So first, I'll be introducing you to biofuels. You may be wondering, what are biofuels? Biofuels are fuels derived from living matter. Although we have fossil fuels, it will eventually be used up. Thus, by using biofuels, fossil fuels can be sustained indefinitely. But why did we choose biofuels? We came across Singapore's International Water Week, and we stumbled upon exhibitions that showcased the uses of biofuels. This sparked our interest, and we decided to explore further and use this topic for our project. Now, I'm going to share some of the exhibitions that we saw. Number 1 shows how food waste is turned into substrate for microalgae production. Used for food supplements and/or biofuels. Number 2 shows how the use of AI can sort circuit board components at high efficiency to recycle or recover resources. Number 3 shows how plastic waste can be turned into permeable road so that water can seep through and into the ground when raining to prevent flooding. Last but not least, number 4 shows how utilizing microorganisms can turn industrial waste into fish food and/or fertilizer. Now I'll be handing over to Herman, who will be sharing the experiments that focuses on food wastage in Singapore.
Thank you, Sitin, for the introduction. We'll now be turning our focus on two prospective projects that lead us to leverage biofuel. One is a bioreactor that utilizes industrial food waste to feed purple phototronic bacteria, which are then collected as biomass for fish food and fertilizer. The second involves using microwave to break down food waste into biomolecules to feed and cultivate a waste for fuel and food production. Both purposes involve recycling food waste into useful product, but they may not be economically viable. That's why, moving on to our purpose statement, we ask, how might we design a low-cost, environmental-friendly way to encourage corporations to recycle their food waste to reduce carbon emission and can benefit while doing so? We first have to understand the relevancy of food waste in Singapore. Did you know that in 2023, 11% of the total waste generated came from food waste? To add to the problem, our recycling rate has declined to 52% over the years. If the amount of food waste generated keeps getting higher and the amount recycled keeps getting lower, we'll be seeing more waste sent to our landfill, which is what we don't want. Furthermore, food waste also impacts Singapore economically and environmentally. A staggering $342 million were lost to food waste alone. To add fuel to the fire, for every 1 kg of food waste, it contributes 2.5 kg of carbon emission to the environment, which is why it's so hot in Singapore nowadays, don't you all agree? This ties us to the next slides. Here, we discuss the impact of global warming brought by the enhanced greenhouse effect, which is affected by the increase in carbon emission. So, what are the impacts of global warming? As you all know, one of the impacts is sea level rise. As you can see in the recent news, the residents of Tulava are already preparing to migrate due to sea level rise, which shows that global warming is already here with us. Besides sea level rise, we also have to be more cautious of increase of insect-borne diseases, as cases of dengue are seen on the rise recently, with 7 reported deaths as of 2024. Singapore will also need to prepare for a hotter winter future, as weather phenomena are intensified due to global warming. Last but not least, global warming also threatens Singapore's food security, with us importing over 90% of our food. A global food shortage will heavily impact us. Moving on to the next slide, we discuss the current context. Singapore is already preparing for a future through the SG Green Plan 2030, which charts Singapore's ambitious and concrete target over the next 10 years. One of the aims is to reduce waste sent to landfill by 30%. This is significant because the Semakau landfill will full in the next coming decade. To tackle this issue, our team wants to turn food waste into biofuel, which is the third option in the waste hierarchy. Now, I'll hand over to Zipin to tell us more about biofuel.
So let's understand what exactly are biofuels. Biofuels are fuels that are derived from renewable, biological resources or biomass. They are produced from organic matter such as plants, crops, algae, and animal waste. And they are also considered as a form of renewable energy, as the biomass used for their production can be replenished through natural processes over time. Using biofuels also bring about several benefits. Only thus using it reduces greenhouse gas emissions as compared to using fossil fuels. It also does not contribute to air pollution. Moreover, it's renewable and sustainable while also being cost-effective at the same time. Some examples of biofuels are bioethanol, biodiesel, biogas, bioethers, biojet fuels, and synthetic biofuels. So, the process that we have decided to conduct an experiment on is methanogenesis. Methanogenesis is the production of methane caused by bacteria or other living organisms. It is carried out exclusively by a group of anaerobic archaea, commonly known as methanogens, which are distinct from bacteria, but are closely associated with anaerobic bacteria. The process of methanogenesis involves a series of biochemical reactions that convert simple carbon compounds such as carbon dioxide, acetate, and methanol into methane, which can then be used to generate energy. Some of the biomolecules that are involved in our system process are carbon dioxide, hydrogen gas, acetate, methane, and hydrogen sulfide.
Methanogenesis is one method for recycling food waste, but there are two additional techniques: harvesting black soldier fly larvae and cultivating purple phototrophic bacteria. Each of these systems utilizes different types of food waste and operates with distinct processes and outputs. Methanogenesis involves a batch process where organic food waste is placed into a digester. Over time, microorganisms break down the waste anaerobically, producing methane, which can be captured and used as a renewable energy source. The process requires careful management of temperature, pH, and other conditions to optimize methane production. Harvesting black soldier fly larvae operates as a continuous process. Vegetable scraps, fly, fruit peels, and other types of food waste are fed continuously to the larvae. As the larvae consume the waste, they grow and are harvested periodically. The output of this process is frass, a nutrient-rich byproduct that can be used as fertilizer for local vegetable farms or as feed for the tilapia fish, which provide an additional food source. Cultivating purple phototrophic bacteria also involves a batch process. Industrial food waste is used as a growth medium for these bacteria, especially designed photobioreactors. The bacteria convert the waste into valuable biomass, which is harvested and can be used as fertilizer in agriculture or as feed for fish. This process requires control over light conditions and other environmental factors to ensure optimal bacterial growth and biomass production. In summary, while methanogenesis and purple phototrophic bacteria cultivation rely on batch processes with distinct waste inputs and outputs, black soldier fly larvae harvesting is a continuous process that integrates waste cycling with agricultural and aquaculture applications.
Materials used for our experiment consist of 5 plastic bottles that were taken from waste bins all around Ngee Polytechnic and were washed thoroughly before being used for our experiment. Pond water that was collected from Commonwealth Secondary School that contained anaerobic bacteria as well as some of the sediment in the pond. Food scraps such as radish and carrot peels that were left over from cooking. Rubber balloons that were wrapped around the bottle to collect any of the gases produced by the bacteria. And finally, tape that was wrapped around the bottle neck to ensure that there would be no gas leaks. Firstly, pond water and sediment were scooped into the bottles. Secondly, an equal amount of vegetable peels bacteria and correlated it to the size of the balloon. And lastly, we noted down any fluctuations in the size of the balloon and checked for any damages to the experiment before we noted down the size change. So here we have the system process of our experiment. Food waste such as discarded vegetable peels go in, and the vessel is sealed after that. And the methanogenesis process will turn the food waste into methane that takes from 2 to 3 weeks. And when the vessel is finally opened, we can collect the methane inside. Here, analysis of our experiment. Phase 1, aerobic decomposition, which takes place from July 1st to July 2nd. On the first day, when the food scraps were added to the bottles containing the pond water, balloons were then attached to capture any gases produced. Initially, there were no noticeable changes to the bottles. However, by July 2nd, the balloons began to leak. This suggests that aerobic bacteria in the bottle were consuming the available oxygen in the sealed environment. In Phase 2, the transition to anaerobic conditions takes place from July 3rd to July 4th. By July 3rd, the balloon stopped deflating, which indicates that the oxygen inside has been depleted, and the appearance of gas bubbles on the vegetable peels suggests the onset of anaerobic decomposition. On July 4th, the balloon started to inflate slowly, which confirmed the production of gases such as carbon dioxide by the anaerobic bacteria. During Phase 3, which was peak anaerobic activity, lasted from July 5th to July 10th. This phase showed significant anaerobic activity, such as 3 out of the 5 balloons inflating enough to be able to stand on their own, more gas bubbles being observed on the surface of the vegetable peels. A putrid smell was noted when one of the balloons broke and had to be replaced, which indicates the production of hydrogen sulfide, a common byproduct of anaerobic decomposition. Carbon dioxide was also likely produced during this phase. And by July 10th, the balloon started deflating slowly, which suggests that the anaerobic bacteria were consuming some of the produced gases. Phase 4, which is depletion and transition, lasted from July 15th to July 17th. The vacuum effect that was observed on July 15th indicates that the gases were being consumed at a faster rate than they were being produced. This could be due to the depletion of easily digestible organic matter, such as the vegetable peels, or a shift in the microbial community. By July 17th, the vacuum effect stopped and gas bubbles could be seen rising from the sediment layer when the bottles were slowly rotated. This suggests a new phase of decomposition, which could possibly involve different types of substrate or bacterial populations. And finally, the last phase, which is Phase 5, methane production, which was on July 19th. The rapid inflation of the balloons, and one of them standing up due to the gas buildup, indicates that the production of methane was underway. Methane is typically produced in the later stages of anaerobic decomposition by methanogenic archaea. The conclusion that we drew from this experiment was that it demonstrates the various stages of anaerobic decomposition: the initial aerobic phase, the transitioning to anaerobic conditions, the peak anaerobic activity with production of CO2 and H2S, a period of gas consumption or reduced production, and finally the final stage of methane production. How we can improve our experiments? Firstly, we could include a control in our experiments to ensure that the gas produced is from the microbes breaking down the food waste and not from any other factors. Secondly, a quantitative way to measure the gas produced over time, such as a gas collection tube, will also be very helpful. Thirdly, using what we learned in IoT to track the rate of change of methane concentration over time. And lastly, the inclusion of a more dependent variable such as carbs or proteins and lipids and dietary fiber, as well as a higher temperature or room temperature to see whether that affects the production of methane.
And with that, we'll conclude our project that biofuels are a renewable source of energy as is done through the process of methanogenesis. Methane is actually produced from this process through food waste and dead matter and is then converted into energy through a process called combustion. This process actually generates a large amount of heat, which is a very good fuel source, which is a very good heat and fuel source. In return, this actually reduces carbon emissions that actually contribute to global warming, as it actually reduces the greenhouse effect. This is also sustainable, as food scraps and dead matter can be easily replenished, which makes it a more environmentally friendly approach as compared to fossil fuels, which release more greenhouse gases such as nitrous oxide into the atmosphere. This project's approach was actually to explore two innovative ways on how we could turn waste into biofuels to clear up landfills, as Singapore is actually limited and we wanted it to be a more environmentally friendly and sustainable approach into generating energy for Singapore, as fossil fuels actually contribute a big amount into climate change. This initiative can also provide cost-saving solutions to tackle climate change. Hence, we actually narrowed everything down to one solution, which was none other than biofuels. So some key points that we can learn from this are actually that methane can be produced in the presence of methanogenic archaea, as these organisms produce methane through the degradation of organic compounds under anaerobic condition. This occurs as most of the oxygen has been used up due to the presence of aerobic bacteria. Hence, we know that organic matter can actually be broken down by methanogenic archaea through the process of methanogenesis to produce methane. We can put this useful information and findings into real-world contexts, such as reducing food wastage that actually accumulates on landfills, which causes landfills to pile up and we all know that Singapore actually has limited land, so this will actually be an issue in the future. So this solution actually helps tackle this large issue that we may have in the near future. So firstly, it can actually help with waste this biofuel solution can actually help with waste management, so they can efficiently convert organic waste into biogas, which can be used as a renewable energy source, helping to reduce dependence on fossil fuels. And this could also reduce the amount of land used due to the ever-increasing amount of organic waste. It can also provide a sustainable agriculture for Singapore, as the byproducts from the methanogenic processes can be used as nutrient-rich biofertilizers, improving soil health and support local urban farming. So let's say if there's leftover waste, leftover food wastage and all those that hasn't been properly broken down by the bacteria, actually use this for natural fertilizers for the plant. So we do actually have to go and use chemicals, whatever, to help with the nutrients of other plants for fertilizing, stuff like that. So it's very sustainable for agriculture in Singapore. So it will actually be a more resource efficient approach as well, as by transforming waste into valuable resources like biogas and fertilizers. They contribute to a circular economy and minimize environmental impact.